In this video, let's talk about finite state machines. Specifically, let's talk about the difference between a Moore machine and a Mealy machine, and let's look at use cases when to use one or the other. So, FSMs, or finite state machines, are fundamental models for designing sequential logic. This can be in software, hardware, in the FPGA, whatever you have. So it's used to also design digital control, protocols, and used extensively in embedded systems. So as you know, there are two major types of FSMs, a Moore and a Mealy. They basically differ in how outputs are generated and the response characteristics. So let's first recall what a Moore FSM looks like. So can you have inputs that flow into the next state logic, that flow into the state memory, and the state memory again has output logic and gives out the outputs. So it's the state memory that controls when the outputs are going to be present, right? So the outputs depend only on the current state and not directly on the inputs. So if you want to change the output, the inputs need to first change the state memory, the state of the FSM, and then the outputs are changed. So that means the outputs get updated only when the state changes. And typically that would happen on a clock edge. So what you're saying essentially is that the outputs are synchronized to the clock. So the next state is a function of the current state and the inputs, whereas the outputs are purely a function of the current state only. In contrast, the Mealy FSM has inputs which go through next state logic to define the state memory. The outputs, however, are determined not only by the state but also by the inputs, right? So the outputs can change either when the state memory changes or when the inputs change. So the outputs depend on the current state as well as the current inputs, and which means that the outputs can change immediately with input changes even if the state does not change. And so you have the next state dependent on the current state and the inputs, and you have the outputs also depend on the current state and the inputs. Now, what are the differences between the two? So here I've tried to put together most of the differences between the two styles of building FSMs. First one, as we just looked at, is the output function. In the Moore, it depends only on the current state, whereas in the Mealy, it depends on the input in addition to the current state. And that naturally means that the output change timing is synchronized with the clock in the Moore, whereas in the Mealy, it can change depending on the input or the clock, so it's not synchronized. Now, with respect to design complexity, because the output only depends on the state, you have very simple output logic. But that means essentially that if you were to design, you'd have to include more states because the output is going to be dependent on the state variable only. The Mealy lends itself to potentially fewer states, however, with more complex output logic. Because of the fact that the outputs only change at the clock edge, Moores are generally less prone to glitches, whereas in Mealy you need to worry about glitches and the impact they might have to your system output. The outputs are synchronized in the Moore. They're not obviously in the Mealy, which means that you need to take care with respect to timings, fast paths, and for hazards. The size, now the Moore looks all nice, but the problem is the Moore typically tends to be larger if you're implementing a logic and tends to have extra states, whereas the Mealy is a more compact implementation. And finally, because of the nature of the way the Moore is designed, debugging becomes easier because the output only change on clear events. Whereas in the Mealy, the debug is tricky because the output can change unexpectedly. So how do you choose which FSM to use, right? So typically you would want to choose Moore FSM when output stability is critical, right? When you have the outputs that need to change only at a well-defined state, for example, in a display signal or a safety control, a Moore is a better option. And synchronous design is desired. So if you need an output which is synchronous to the clock edge, a Moore is a better design choice just because It is predictable and hence timing analysis becomes easier. Moore also lends itself to design simplicity and easier debug, again primarily because the output is driven only by the current state, and so they're easy to verify, and the outputs are generally glitch free. Examples would be traffic lights, sequence controllers, etc. typically lend themselves to Moore implementation. You choose a Mealy FSM if you want a fast reaction to input changes, right? So suppose you have a sensor and you want your system to respond quickly to it, then you want to probably think about a Mealy FSM if that's the parameter of interest. So it enables lower latency control. And suppose state minimization is something you care about. Suppose you are building a very complex system and you don't have the luxury of building a lot of states, then Mealy typically tends itself to lower number of states, so you can implement them with a fewer logic, if you will. Outputs, if early outputs are beneficial, again, that's something you can think of using Mealy. So for example, protocols or handshakes which require immediate acknowledgement lend themselves typically to Mealys. And so you have examples like serial protocol controllers, input debouncing, high-speed data processing, all of which will lend themselves more to Mealy because latency is important in those applications. Typically, what one uses is neither Moore and Mealy. What we do is a hybrid approach. So we handle the controls are handled using Moore style states, whereas fast paths or reaction to inputs are typically handled using Mealy logic. So what happens if you make a wrong choice? So if you put a Moore machine where a Mealy would be needed, then your outputs are basically going to react too slowly, leading to longer latency, timing windows having issues, and you are implementing something which requires more states. So it might increase power, area, verification overhead, etc. On the other hand, suppose you had suppose you implement what could potentially be a Moore application with a Mealy machine, you got to have to worry about the output glitches because those happen in the Mealy implementation. And if the input signals have hazards, those are something you need to take care of. The debugging complexity increases because there are a lot of dependencies on the output, and so you need to test for all timing conditions here. So debugging is hard, and for safety critical applications, they may violate design constraints. And overall risks, if you look at in general about FSMs, these are things which you have to do anyway, whether you're doing Moore or Mealy, is that you need to worry about functional errors. So in real world timing, the system may behave incorrectly. That's something you need to test for. And as we discussed in the flip-flop case in another video, you need to worry about metastability and glitches, and system malfunction due to glitches or timing hazard need to be carefully characterized. And finally, because of this, you might fail standards or certifications, so safety and compliance should not be compromised when you're designing a good FSM. So what are the design best practices typically? So first thing is analyze the required timing and confirm or figure out if your system needs inputs to change synchronously or immediately. So that gives you a first clue as to which style would work for you. For safety, displays, actuators, etc. prefer a Moore kind of a design, whereas for fast protocol, latency-driven applications, as I mentioned, a Mealy might work better for you. And it's always a good idea if you're implementing a Mealy FSM to synchronize the external or asynchronous inputs. That way to ensure that you reduce the probability of glitches in your design. And finally, carefully validate. This is true for all FSMs. Validate outputs with simulation. In Mealy, it's especially critical to do this so as to catch any unintended hazards or violations that you might have in your design. And as I mentioned before, typically in real world, you end up using hybrid FSMs. And as long as you're partitioned it properly, you should be able to take the advantages of both the Moore and Mealy for your design implementation. So let's now run through a couple of applications which I've ID'd, just showing you how an FSM would be designed. Again, remember, this is not necessarily logic implementation. You can also think of it in terms of writing code, in terms of implementing a RTL, in terms of coding up on an embedded system, whatever you might have. So if you look at a USB flash drive or a storage controller, you typically have an idle state, which once a device is inserted, depending on its input, it goes into enumeration. Once the enumeration has succeeded, it goes into a ready state. If the enumeration fails, it goes into an error handling state, which you need to confirm. In the ready state, again, depending on what as a user you give a read or write, you go into the transfer mode where data transfer occurs. Once it's complete, it goes back into ready for more data transfer if needed. If the transfer fails, you go back into error handling, and that is generating the right messages back to the user. And then you normally have a recovery or a reset option, which resets the system out of error handling and brings it back to the idle state. In addition, you also have an eject command which pushes it into an eject state, and the eject state allows you to remove the flash drive and then push the controller back into its idle state. Now, typically this functionality is embedded in firmware, or sometimes dedicated logic is used in the controller. You can also add versions and more states for power management, firmware update, or secure arrays. And normally this is implemented in a Moore implementation because outputs which include data transmission or line status are driven primarily by the current state. Because of this nature, we typically implement the controller as a Moore. Now let's look at another application. This comes from the world of memory. So if you're looking at the DRAM memory array access control, again, you start off with a rest state or idle state, and when you get a read or a write request, you send the system or the controller into its row activate state, which once the row setup is done, it goes into column access. In the column access, then if it's a read, the column access then goes into its sense circuitry to sense the bit stored in the DRAM. If it is a write operation, you send it to a write state where you write into the DRAM. Once the write is done, you need to precharge the bit lines. So the precharge, you send it into the precharge state. After the read is done also, you send it into a precharge state. And once the precharge is complete and detected, when the precharge is ready, you send it back into the idle state. So here again, typically what we use is one hot or encoded states in the memory control logic, typically implemented as an ASIC. If you're looking for best patterns, MBEST integrates separate FSM for various test patterns and error detection. So on top of this, typically when you're doing reliability studies, you want to use a different FSM to basically test for patterns. You can also think about using addition states for error correction, refresh, address remapping, etc. Again, this is mostly a Moore implementation because memory signal outputs typically depend on the current operation state. And so to ensure the process timings are met across process corners and no glitches occur, we typically refer to Moore because a Moore tends to be more predictable than a Mealy. Let's look at another user application. So you can talk about a camera autofocus that's there on your phones. Again, start with an idle state. When the shutter is half pressed, you're doing an autofocus, so it's searching. Once the focus is locked, it goes into its focus state, and then the shutter is pressed and it goes back into idle. If the focus is lost, then it goes back into searching and continues till focus is found. If there is a timeout that occurs, then you send it into an error state, and the error state is again reset back into the idle state. So again, very similar to the previous applications. Typically, these are implemented using state tables, like how we saw in the Verilog videos. You can also think about advanced systems which use additional states, say for low light operation, for face recognition, etc. Now this would be normally a Mealy implementation simply because the output is linked to both the state and the sensor input, and because you want real-time dynamic response, a Mealy is a better option to implement this FSM. Then let's look at a very generic robotic FSM. This can go into washing machines, this can go into drivers, simple robotic FSM. Again, an idle state based on a command, initialized, typically you send it into an initialized state, which is waiting for inputs, and then once it's ready, so this is kind of the ready state, then you have a trigger Now that trigger can either be sensor driven or can be input driven, and then you send it off into the operate or a move mode if you're thinking about a simple robot that's moving on a path. And then once that operation is done, you send it into a complete state, and the complete state then goes to reset and goes into the idle state. And for every state you have a fault, and that fault pushes it into an abort and error state, which requires you to go and check what the issue was, right? Again, these typically are implemented as PLC, very simple way of doing it with low hardware, or using function charts into a controller. Normally also can implement it directly using a software module with real-time OS support. Now here, safety overlays can be added, and you can have an emergency stop in case you want a very safety controlled environment. And typically this, again, depending on what the application is, whether it needs to respond quickly to sensor inputs or not, you can choose to either implement it as a Moore or a Mealy. So a Moore would be typically for step sequencing. If you're predictable, if you know exactly what the flow is, then the Moore would be better. And for collision kind of triggers, etc., you want to use Mealy because you want an immediate reaction to the sensor input. Let's look at another example. Say you want looking at secure smart cards. Again, you start off with an ideal state. When you insert the card, it goes into card detected mode. Once the card is verified, it goes into an authorization start mode. You enter the PIN is verified. If the PIN verification is okay, then it goes into data transfer, and then you can transfer data. And again, like everything else, you will have a reset state here, and the reset state is basically pushing it when it's done with either processing, right? And this is again implemented either using programmatic FSM. You can also add security overlays here again for lockout alerts, any other inputs or outputs you need to add, depending on what kind of risk appetite you have for an application. And typically for security critical states, right, it's useful to implement as a Moore simply because the state transitions are control the outputs, and so intermediate outputs don't tend to leak out. So a Moore FSM typically for safety critical is recommended. So to conclude, picking Moore and Mealy is relative. You need, with experience, you'll begin to figure out which one works for you. A general rule of thumb would be that Moore FSMs are favored when outputs should remain stable at well-defined state changes. So safety applications, protocols, power controls, debugs, etc. would go with the Moore application. A Mealy is chosen when fast output responses are needed, sensor processing, etc. And finally, as I discussed in the beginning, typically we use a hybrid application, and that uses a Moore for primary control flow and Mealy for output logic at specific critical points for responsiveness.